Hi everyone. In today's session, we will be discussing a problem about circular motion. Let's begin. So here in this problem, we have a rubber bung of mass 200 grams, and then it's tracing a horizontal circular path, and then the string makes an angle of 56 degrees with the vertical. So for this problem, we are asked to solve for the tension. That's gonna be T, angular velocity, omega, and then the time it takes to make one complete revolution, which is basically the period. So let's list down first the given information. We have the mass, and then express the 200 grams in SI base unit. That's going to be 0.20 kilograms. We have the radius of the circular path. So that's going to be 0.40 meters. And then theta, which is 56 degrees. Now, next step that we need to do is to make a free body diagram. Now, this free body diagram will help us to imagine the problem. Imagine the forces acting on the bung. So let's begin with the force that acts along the string, which is this force. And obviously, this is the tension. Next, we have the weight of the bung, W. Now, the tension is at an angle, so we must resolve this into its components. So we have T sub y as the vertical component of the tension, and then T sub x, horizontal component. Now, let's also label the angle. It says here that the angle was made with the vertical, so theta should be here. Okay, now that we have listed the given as well as made a free body diagram, let's now proceed in making our working equations. So let's consider first the forces acting along the horizontal. So on our free body diagram, there's only one force acting along the horizontal, which is the horizontal component of tension. So the summation of forces along the x will be equal to T sub x. Now, remember that this bung is moving in a circular path horizontally, which means that it experiences a net force. Remember that any object that traces a circular path experiences a net force, which is the centripetal force. So we will replace this expression for the net force along the horizontal with the centripetal force F sub c. So Fc is equal to T sub x. And usually we have two equations that we commonly use for the centripetal force. That will be mv squared over r as well as mr omega squared. But since in the question, one of the quantities that we are to solve is omega, then let's use that expression or that expression for centripetal force. So mr omega squared is equal to, now I've replaced t sub x with t sine theta. Why? You can actually move the t sub x over here, allowing you to form a right triangle. So with respect to this theta over here, t sub x is actually the opposite side or on the opposite of this angle. So in this vector triangle, or using this vector triangle, we now have this working equation. Mr omega squared is equal to t sine theta. So that's it for the forces acting along the horizontal. Now, let's move on to the forces acting along the vertical. Now, if you look at our diagram over here, there are only two forces acting along the vertical component of tension and the weight. So, summation of forces along the y will be tension, T sub y, or the vertical component of tension, minus omega. By convention, since T sub y is directed up, it's positive, and since weight is directed down, it's negative. So that's the reason why we have this negative sign over here, or the minus sign. So as this bung is moving, it neither moves up nor down. So we can say that the net force along the y direction will be 0. And transposing weight to the other side, we'll now have weight is equal to t sub y. So we replace weight with mass times gravity, and then t sub y with t cosine theta. Again, using this vector triangle over here, t sub y is side adjacent to the angle. Okay, so we now have our given. Again, we list down our given and then our working equations over here. Let's start solving. First thing to solve will be the tension. Now, looking at our working equations, we'll be choosing which equation will be better in solving, or better to use in solving tension. Now, we must make sure that only tension is the unknown in the equation for us to be able to use that equation. So if you look at the first working equation, m is given, r is given, but omega is unknown. It's actually one of the questions being asked to solve for omega. So in this equation, we have two unknowns, omega and tension. That means we cannot use this equation. So if we move to the second working equation, we have mass, that's given. G is the acceleration due to gravity, so that's a constant. And then theta is also given, that's 56 degrees. So t is the only unknown. That means we can use this to solve for t. So manipulating this equation, we'll have t is equal to mg over cosine theta. And substituting all the values, we'll have the value of tension to be approximately equal to 3.5 newtons. Okay, so we're done with tension. Next, let's solve for angular velocity. Now, going back to this first equation over here, we have already solved for t, tension. And since theta is also known, we can use this to solve for omega. So manipulating this equation, this gives us omega is equal to the square root of t sine theta over mr. And we just have to substitute all the values to get a value for the angular velocity of around 6.0 radians per second. And then lastly, we are asked to solve for the period. Now remember, um, angular velocity is equal to the angular displacement over the time taken. Now, for one complete revolution, the angular displacement will be equal to 2 pi. And then, of course, the time taken will be the period. So, angular velocity is equal to 2 pi over t. And then manipulating this equation, we will be able to get a value of around 1 second for the period. So that's it. That's how we solve this problem. So I hope everything's clear, guys, and thank you for learning with me today. See you next time.